Exercise set 1.4. Applications. Two-variable linear systems of equations. Standards of solutions. Define all variables. Explain the source of any newly introduced equation. Assess the correctness of the solution by performing two types of checks: a check of the math problem solution and a check for sensibility in the real world. Of the two checks, the latter is the more important. Be reminded that the most likely source of error in an application problem lies in the translation from the real-world problem to the math model problem, thus the importance of a sensibility check. Calculator usage is required. Exercise 9. Two identical inlet pipes allow water to enter into a 500-gallon tank. A single outlet pipe carries the water away to irrigate farm crops. When all the pipes are open, it takes 27 minutes and 24 seconds to fill an empty tank. When one of the inlet pipes is closed, it takes 1 hour and 12 minutes to fill an empty tank. Determine the flow rate for one of the inlet pipes. Round final answer to 3 significant digits. Okay. Let's think about defining our variables here. Since the question asks us to determine the flow rate for one of the inlet pipes, we imagine that will probably make a pretty good variable in this question. Alright, let's go with that. Let's let x equal flow rate of, and we'll be careful, 1 inlet pipe. And when you're defining variables, it's good to put the units of measure right along with your definition. In this case, let's see, we have gallons as a obvious unit for volume. For time, let's see, there's minutes, seconds, and hours all running throughout here. I suppose gallons per minute might be the most convenient here. You can choose anything you like, but once you choose it, you need to stay with that throughout your math formulation. Okay, so here, the units of measure chosen to be gallons per minute. Another variable here, okay, would have to be the flow rate of that outlet pipe. So let's let y equal the flow rate of there's only one of it, the outlet pipe. Gallons per minute there as well. Okay. Now, let's see, what can we do for any kind of source of equation here? Says when all the pipes are open, it takes 27 minutes and 24 seconds to fill an empty tank. Okay, we can work with this and get something going. First, maybe we just take the sentence, all pipes open takes 27 minutes 24 seconds to fill an empty tank. Okay, now there's another basic principle we can use here, and that is that when you have fluids flowing, volume equals rate times time. As long as your rate is constant, you have this basic relationship for fluids. Okay, how can we use that here? Well, the volume, that's the empty tank getting filled, that would be a 500 equaling to, now the rate. What do we do here? Well, we have two inlet pipes open, so their rates add together. Now an outlet is actually draining away fluid, so we would need to subtract that from the rate. So the net rate of these pipes would be 2 inlets, 2x, minus 1 outlet, y, and then times time, 27 minutes and 24 seconds. We're choosing minutes to be our unit of fundamental measure in this problem, so now we stay with minutes throughout. So we'll write this as 27 plus, 24 seconds, 24 over 60 seconds, that much of a minute. And this does provide us with an equation, equation 1. Okay. Now, something else. Okay, a similar idea. When one inlet pipe is closed, it takes 1 hour 12 minutes to fill an empty tank. Okay. 1 inlet pipe closed takes 72 minutes, 1 hour and 12 minutes to fill an empty tank. Okay, well, back to that same principle. Volume equals rate times time. The volume is again that 500-gallon tank getting filled. The rate, okay, one inlet pipe is closed. So now we have one inlet pipe acting as positive flow, minusing the outlet y. So there's our net rate of flow in this situation, and the time, that is the 72 minutes. And this would bring us an equation 2. As we look over the math problem here, equation 1 and equation 2, we find this equation is linear, 2 variables. So is this one. Okay, so we can say here, can observe that equations 1 and 2 constitute a linear system of equations, 2 variable. Alright, so we are really proficient to this, and let's go ahead and, since the numbers look a little messy, I suppose we could go to a calculator solution. That first equation, let's solve for y. Okay, so we need to divide both sides by this number here, 27 and 24 over 60, and then we should subtract 2x from both sides, and then multiply both sides by -1. I suppose if we did that, we'd have y1 equaling, okay, we have the 500 over 27 plus 24 over 60, and then we were going to subtract the 2x and then multiply by -1, which then makes it look more like 2x minus this when it's completed. Okay, let's go to the second equation and solve for y in this case also. Could divide both sides by 72, subtract an x, multiply both sides by -1. Y sub 2 could equal, let's see, 500 over 72. Then complete it as so. Alright, looks like it's time to head to the calculator. Okay, at the calculator, go to the y equals 2 edit screen, and our y1 is 2x minus 500 divided by, need some parentheses here, 27 plus 24 over 60 parenthesis. Okay, our y2, we've got x minus 500 divided by 72. Okay, now, in getting ready to graph this x here, this represents a flow rate of one inlet pipe. Okay, what sort of numbers could it all be possible here? Since it takes, let's see, 24 minutes and 24 seconds to fill an empty tank with everything open, we don't know too much about the outlet pipe at all. Okay, maybe we just start off with an arbitrary guess almost, and then see what the graph looks like, change our mind thereafter. So right now maybe we just say 0 to 100 for x, without giving it too much further thought. 0 for x min, and 100 for x max. Okay, and then we go with a zoom fit. Okay, what we are looking for is in sight. Looks like a single point solution. Let's go ahead and calculate it. Second, calculate, intersect. Okay, that could be a first curve. That could be a second curve. As far as a guess goes, let's go back this way. Alright, we know it was about in there somewhere. That's good enough. Enter. Alright, we have these numbers here. Let's go back to our paper and start to record a conclusion. Okay, so first of all, maybe we could just say the calculator has given us this x equal to 11.3. Now we're rounding everything to 3 significant digits in the end. This is the time to suppose do that. And meanwhile, the y is number-wise here equal to 4.36. Now, what is it we need to record? The question asks us to determine the flow rate of one of the inlet pipes. We chose x to be the flow rate of an inlet pipe. So now we're ready to make a conclusion by interpreting this. Okay, let's put on the units of measure and say what this means. The flow rate of one inlet pipe is 11.3 gallons per minute. Okay, it's our big conclusion. Prominent cloud around that. Now let's start checking things over. First, just the math itself. See if that looks okay. For math check, it's time to go back to those original equations. So we will substitute into the original equations. See what goes on there. Let's see, looking back at those original equations, it's the right hand side that will be what the calculator will compute here. So we're looking for a 2x minus y multiplied by 27 plus 24 over 60. See what happens there. Secondly, we'll take a look at the right-hand side of the second original equation, x minus y times 72. See what happens there. Back to the calculator. Okay, here at the calculator, going back to the home screen, let's try out that left-hand side of the first equation. So we get the parenthesis 2x minus alpha y, and then the other factor, parenthesis 27 plus 24 divided by 60, parenthesis. Okay, let's see. Nice, 500. That checks that one. Okay, now for the right-hand side of the second equation, parenthesis x minus alpha y, parenthesis, times 72. Enter. Okay, very nice. Let's go back to the paper. Okay, so this came out to be a 500, which is just what we see in the original first equation. Check. This came out on the calculator to be 500, which also matches the second equation's right-hand side. That's a check. Alright, now on to the sensibility part of this check. Okay, how can we look this answer over here as far as being sensible at all? Alright, let's see. We got this 11.3 gallons per minute as an inlet pipe. Okay, we could try something like this. What if we imagine ourselves having only the inlet pipes open? How long would it take to fill a tank? So now here's a real, what I'm doing is we're trying to create a very simple situation which requires minimal amount of math to do a calculation and see if it's consistent with everything else that's going on in this question. So, okay, so consider only both inlet pipes open. Okay, so how long would it take them to fill a tank? Time to fill 500 gallon tank. We can go back to the idea that volume is rate times time, or in other words, time should be volume over rate, and here that would be 500 divided by, okay, just two inlets. That would be 2 times our 11.3, 22.6, and see what that is on our calculator for a moment. Okay, simply a 500 divided by 22.6. Okay, so we're looking at this 22 minutes here, about 22.1 minutes. Okay, now, is this consistent with everything else? The time that it takes to fill the tank with only inlet pipes open, we expect should be less than any other time in this given information, which always had outlet pipes open at the same time, working against us. And this is consistent with the idea that this time is less than the 27 minutes plus that it takes to fill the tank when there is an outlet pipe open as well. Okay, so this is consistent with the expectation that this time be less than if an outlet pipe is also open. Okay. So, since that makes some sense, we've at least challenged our answer a little bit with something fairly simple to give it a feel that this really is correct overall. Exercise 11. An architect is designing the horizontal cross-section for a future 60-story building. As illustrated below, the cross-section is to consist of a central rectangle flanked by a pair of equilateral triangles. The perimeter is to be 1,000 feet. For aesthetics, the sum of the areas of the triangular regions is to equal the area of the central rectangle region. Determine the dimensions of the central rectangle. Round to the nearest inch. Okay, let's see for our variables. Well, there's this diagram sitting here. We might as well use this as a basis to decide how we want to define variables. It's the central rectangle that's of the primary concern, so perhaps we could label this dimension here as x, and this dimension here as y. So we can begin by saying, let x, y be the rectangle dimensions illustrated. And looks like feet would be a convenient unit of measure there. Okay, let's see, what have we got for information here that turns into an equality or something of that nature? This sentence. The perimeter is to be 1,000 feet. Okay, let's translate that. The perimeter is to be 1,000 feet. Alright, let's look at this diagram. Perimeter's all the way around here. If this is y, and these are required to be equilateral triangles, that means their sides all have equal length. Then we furthermore know that this is y. This is y. So is this, and so is this. Okay, then as we travel around a perimeter, looks like we have a total of 1, 2, 3, 4 y's and 2 x's. Okay, so the perimeter, 2x plus 4y, equals 1,000. Okay, got an equation? Could call that equation 1. As you look at this equation, you may be tempted immediately to divide both sides by 2. Alright, x plus 2y equals 500. And so this will be equation 1a. Alright, let's look at the other information, see if we have some more. For aesthetics, okay, the sum of the areas of the triangular regions is to equal the central rectangular region. Okay, let's take that. That'll be good for us here. Sum of the areas of the triangular regions. Sum of areas of triangular regions equals area of rectangular region. Alright, let's see here. Sum of areas of triangular regions. There's 2 triangles here, right? Okay, so just basically getting things started. 2 because there's two triangles. And then what about the area of a triangle? One real basic formula that you probably should have memorized is area of a triangle is 1/2 base times height. Okay, and here's an equal sign, and over here is area of a rectangular region. Well, that's just length by width, which we can surely see here is x times y. Now we need to do some work here. This base here, for either of these triangles, look at this one here, the base could be considered y, in this case here. Now h. Okay, now h is the height, or more formally the altitude, of a triangle. So here we are with h. It's in here. What can we say about this? Okay, this triangle is equilateral, so then each angle must be the same. So here is 60 degrees, and here is 60 degrees, and all of here is 60 degrees. Now, since we've bisected this angle here, this right here is actually 30 degrees. Okay, now for a 30, 60, 90 degree triangle, the sides have well-known ratios, namely sides have ratios 1 to the square root of 3 to 2. 2, of course, is the hypotenuse. 1 is the shorter side. The square root of 3 is the other side. Now, this will imply something for us here. Let's look at this triangle here. Here's h. Here, since this is all of y, half of it is then y over 2. Right in here. Okay, so we could say that, let's see, we can get a ratio set up between h and y over 2. We could say that y over 2 is to h as is shorter side to middle side. That would be 1 to the square root of 3. And from that, we can have that equate cross multiples here. H equals y square roots of 3 over 2. Okay, well, this is nice. This gives us a much nicer expression for this h here. We need it in terms of y, so now we have it. Y square roots of 3 over 2. Okay, now let's kind of simplify what we've got developing here. 2 1/2 cancels. Here's y by y and square root of 3 over 2. Alright, so now we're sitting here with y squared, square root of 3 over 2 equaling to x times y. Okay, we could call this equation 2. As you look at this equation 2, you may decide right away this could simplify further by dividing both sides by y. Now that leaves us with y square root of 3 over 2 equaling to just x. Okay, equation 2a. Now looking at our math problem here, which consists of this equation 1a and this equation 2a, notice it's indeed a linear system, two variables. Okay, so observe that equations 1a and 2a constitute a linear system, two variables. Okay, let's put them together here and consider solving our system. X plus 2y equals 500, and here is, let me take 2a and put it into standard form. So I'll subtract y squared to 3 over 2 from both sides and have this look like x minus y squared to 3 over 2 equaling 0. Okay, well, this system is actually perhaps so simple that I might as well solve it manually, at least for this point. And going here, we could take this equation, subtract this one from it. So x minus x is 0. 2y minus negative y squared to 3 over 2. Okay. 2y plus y squared to 3 over 2 equals 500 minus 0. And now we could factor the y outside here. And then we could divide both sides by this factor here. Perhaps you want to simplify this complex fraction, multiply it by 2 over 2. Okay, now, although this is exact is not of real interest to someone trying to build something here. They need numbers, and this question in fact specified that we round to the nearest inch. So let's start taking this exact y here and seeing what it is in terms of a decimal number, and realizing that this is in terms of feet. So we have to also convert the fractional leftover into inches. It's time to go to the calculator. Okay, here at the calculator, let's perform this arithmetic needed to compute y. We need here 1,000 divided by parenthesis 4 plus second square root of 3 out from the radical sign, and another parenthesis to seal off our denominator there. Let's enter that. Okay. Now, before we go further, let's store this in y so we have it for future math checking and whatnot. So we could go here and store to alpha y. Enter. Okay, it's in there. Now, when we record our answer, although we see the 174 point so-and-so feet, we need to have this to the nearest inch. So let's continue here. Let's subtract off that 174 feet minus 174. Now this leftover is the part we would turn into inches. Now this is feet, so the conversion factor is 12 inches per foot, meaning we need to multiply this by 12. Okay, so that will round to about 5. So our y dimension will be 174 feet 5 inches. Next, we may want to go ahead and get the x that goes with this. We could use one of the equations of our system. That'd be pretty easy. I suppose the second equation looks like a very simple source here. And so we can look at the x plus 2y equals 500. And then from that, it's simply a matter of x equals 500 minus 2y. So let's compute. 500 minus 2 alpha y. Okay, now with this x, we also will need to have the inches extracted from this leftover here. we see the 151 feet. It's that leftover that we need to convert to inches. Okay, so let's, as before, subtract the 151. And now we'll just convert this feet here to inches times 12. All right, that's going to round to about 1. All right, right now let's go back to our paper and record our results up to this point. Okay, so noting the calculator's arithmetic here, we're ready to start making our conclusion. It looks like in this case our conclusion is going to refer back to our diagram that has x and y labeled, so it will be clear what that it means here. So we can make a sentence saying the rectangle dimensions are x equal to, we have here 151 feet 1 inch, and y equal to 174 feet 5 inches. And we should probably point out here C diagram, because it's not clear alone from the sentence what that means. Okay, it's our big conclusion. Time for a prominent cloud around this. Okay, now let's go on to the checking of all this. Let's start off with the just checking out our math here. Okay, it's time to substitute into the original equations. Now let's see, if we look at the original first equation, the left-hand side was 2x plus 4y. Let's see how that comes out on the calculator. The second equation, looking for its original formulation. Okay, now it has, well, variables on both sides of it, so, okay, we'll say here, let's see, to organize this a little bit, here's equation 1. Here can be equation 2 here. Now we'll take this left-hand side and a right-hand side, since the equation has variables on both. And we can say here the right-hand side, which equaled, it had y squared, square root of 3 over 2. And the left-hand side was equal to x times y. Alright. Let's take this and go to the calculator. Okay, back at the calculator. Maybe we clear the screen here. Oh wait, we have not stored the that last entry that we needed into x. Okay, you know what? We can do that. Let's go second entry. Second entry. Second entry. Alright, this is what we use to actually compute the x. Let's go ahead and get that number, and this time we will store it to x. Okay, now we're ready to perform our checks. The first original equation, 2x plus 4y. Let's see what happens here. 2x plus 4 alpha y. Go. Ah, good, 1000. Just as in the first equation, right-hand side. So that's in order. Let's start the right-hand side of the second equation. We have alpha y squared times the second square root of 3. Terminate the radical sign. Now we can divide this by 2. Enter. Okay. Now let's get the left-hand side of the equation. We want the product of x alpha y. Enter. Okay. This is looking good. Let's record our results on paper. So we did the 2x plus 4y, came up with 1,000 on the calculator, just as in equation 1. That's a check. This number here, it came out to be, well, approximately equal to 26,358. And the left-hand side also came out to be this same number. Okay. These two the same? That's a check. So, at least as far as the math goes, we look successful there. How about sensibility? Does this these numbers make any sense to us? When you have completed a very graphic, geometric, I should say, kind of a question, one of your best things you want to show someone is a scale diagram of the results. So let's try that here. Scale diagram. Let's see, to fit in this remaining little bit of paper we have here, maybe we go with 1 centimeter equaling 1 foot. Or rather, 100 feet, I should say. Okay. Now, we have here our y is 174. So we can maybe come in here and sketch a 1.75 centimeter line there. Now, let's go in this direction, and let me come up here, sketch a 1.51 centimeter x. Come down here and do the same thing below. Okay, putting in the other y at 1.75 centimeters. It's about there. Now, the triangles, equilateral, maybe to assist us in sketching them, let me draw the midpoint of this. Let's see, 1.75, that'd be about 0.9 there. On this side, about there. Just a very light little bisector line here. Now I want to draw those other two sides of the equilateral triangle. So I want sides that are 1.75 centimeters and want them to terminate on this line. So it's about that. Okay. Same thing on this side. And one more. Okay. So here we have our diagram of this building base, and what we're looking for here is for things, are they going to, does it look sensible for the base of a building, or do these dimensions create something that's just ridiculous? And here, for the base of a building, this seems to look, pretty reasonable. I think it looks, reasonably stable. So that if it was extremely skinny, we'd think, oh, this building will just topple over. Here, has a fairly solid-looking support base to it. So here, we might say, appears reasonably stable. And by the way, this was the x here, which maybe I'll put this down as its dimension, 151 feet 1 inch, and this these y dimensions here, 174 feet 5 inches, 174 feet 5 inches, like so. And since this looks pretty stable, we'll consider that a check. The answer seems sensible as well as passing the math check. So it looks good.